Welcome to day 4, where we keep playing games with elves, and today we trying to win big by playing scratch cards. As we arrive on a new island in the sky, an elf runs over to us. If we help him with something, then we can borrow his boat for our journey. We are asked to help the elf, who has a very big mountain of scratch cards, figure out which of his scratch cards have won anything. Scratch cards are presented to us in the form of single lines, where every card has a card ID, followed by a few numbers that are the winning numbers, which in turn are followed by the actual numbers that we have. If one of our numbers is winning, then our card is worth 1 point. For every next winning number, our card value doubles. Now, if we look at all the cards the elf has, then how many points are those cards worth in total? Let's look at 2 examples. On card number 1, we see that we have 4 numbers, as marked by the green circles, that are winning numbers. So in this case, where we have 4 matches, we assign the card a value of 8. In this second example, we only have a single number that is a winning number. Thus, our card is worth only 1 point. Now is a good moment to pause the video and give this problem a shot. You can get your own input for today's problem at adventofcode.com. Be sure to check it out. I hope you agree that the solution of today's part 1 is fairly straightforward. Per card, we need to parse the data, and then we compute the number of points that this card is worth. This is expressed in the following code. First, we initialize our total to 0, and then for every line in our input, we execute the parse card function. This gives us back 2 groups of numbers. Firstly, the winning numbers. Secondly, our numbers. Then lastly, based on those numbers, we compute the card value and add it to the total. There are many ways to parse the data of the card, but I went for just calling split on the markers and then parsing the numbers left and right of the pipe symbol. At the end, we return the numbers as sets, in part because we only have unique numbers anyway, but having sets helps us greatly in solving the next subproblem. See this example for why this is. Suppose we have a game with the winning numbers 1 and 2, and our numbers are 2 and 3. If we have these 2 groups of numbers as sets, then we only have to look at the intersection of those 2 sets to figure out how many of our numbers are winning. And this is exactly what our compute card value function makes use of. It takes in 2 sets and computes the overlap, more commonly known as the intersection. Then we store the length or size of the overlap in a variable. If this variable is 0, then we just return 0. Else, we can actually return 2 to the power of n-1. The reason this works is because 2 to the power 0 is 1. From that point on, the sequence starts doubling. This is exactly the same as how the points work for the cards. And that's it already for part 1. Let's move on with part 2. Eventually, we realize that the rules of the scratch cards are written on the back of the cards themselves. There actually are no points. Instead, scratch cards cause us to win more cards equal to the number of winning numbers that we have. More specifically, suppose we have 3 winning numbers on card 10, then we would win a new copy of each of the next 3 cards, those being cards 11, 12, and 13. Note here that we are told that it is guaranteed that we won't ever win a copy of a card that does not exist. So suppose have 100 cards in total, then the last card, number 100, can't contain any winners by definition. Otherwise, we would win a copy of card 101, which does not exist. Now this game is finite. If we play until we have no more cards left, how many total scratch cards do we then have in the end? Because I think that our example here with 3 winning numbers on card 10 says most of what can be said, I shall not dive into detailed examples. Let me know in the comments if you agree or not. And for now, let's jump to the solution. Theoretically, we can simulate every card one by one, but let's have a look at something that is a bit faster than that. For our solution outline, we do the following. We want to store our cards in dictionary named cards, where the card ID shall be the key and the numbers the values. Then, for every line in the input, we iterate using enumerate, which gives us an index as well. Then let's use this index instead of the actual card number. For the rest, parsing the cards is the same. Note that we don't care about the real index of the cards, as long as they appear in the same order. So starting our indexing at 0 is convenient for a follow-up step. At the end, we of course need to simulate our card game based on the card data that we parsed. Now let's take a look at that simulation function. What we want to do here is keep track of how many copies we have of each card. Since we get one copy of every card at the beginning, we create a list of ones in card count. Then we denote all those initial cards as the number of new cards that we have, which is also the total that we have thus far. Then, while we keep having any number of new cards, we simulate one round of the game where we calculate how many cards we get as winnings based on our current cards. We do this using the obtain next cards function, which we'll dive into a bit later. Assuming that the obtain next cards function did its job, then we have an updated list of card counts. The values in that list represent how many cards we have for every ID, and the sum of this is the number of new cards which we have. We add these new cards to our total, and we prepare for the next round of simulation by updating the card count list with our new list. At the end, we of course return the total number of cards which we had during this entire game. Now, the trick for obtaining the next cards efficiently is to not update on a per-card basis, but instead to do all the cards with a certain ID at once. In this example, we only have 3,000 cards with ID 1. Now, suppose that we had 2 winning numbers on this card. Then we would get a copy of card ID 2 and card ID 3. If we would solve per card individually, then we would have to check our winnings and update the cards 3,000 times. So let's batch them together instead. The function itself then initializes new card count to be 0 for every card ID. Then, for every card in our dictionary, we check, based on the ID of a card, if we have any cards. The value can be computed then once, regardless of how many cards we have with that ID, and we update the next card count list accordingly. The range for updating is of course starting from I+1 up to I+1 plus the value that we computed. If this value was 0, then the range is 0. Suppose we had made our cards start at ID 1, then we would have to modify this range to match the list, or the list would have to have padding. So starting at 0 was a nicer solution in my opinion. As a final point, of course, the compute card value function no longer has the complexity that it had before. It only needs to return the size of the intersection. And that's it once more. You should now understand a way to get the 2 stars for day 4 of Advent of Code 2023. I hope you like the content, and I look forward to showcase a solution for tomorrow's problem.